Okay. Welcome, everybody. We are coming to the end of the semester. So from my count, there are 4 lecture times remaining that I have. So 2 today, 1 tomorrow, makeup lecture at 3 o'clock downstairs, and then 1 next Tuesday. And then I think classes are finished. So it's a very short time. And I'm not going to introduce too many further topics. And I'm mostly going to try to do example problems. So there's some really good ones at the end of chapter 13 that really capture a lot of what we've studied in the course so far. And I started one of those in the prior lecture, and it was about different ways of cumulative creep over time. So especially when there are different temperatures and different stress levels involved. So I'm going to finish that example problem, and then I'm going to talk a little bit about creep, combined creep and fatigue, right? So if you have high temperatures that are held under, components held under stress for a long time, but then those stresses are cyclic, how do we combine those two? And so there's a really nice example problem at the end of the chapter for that. So I ended last time sort of partway through problem 1311, and we were given sort of a chart that had a bunch of curves on it like this at different stress levels. And so you can see the stress levels in PSI are given for each series. So 1,000, 2,000, 3,000, 4,000 PSI. This is for alloy X, so we don't know exactly what it is, but it's experimental data we were given. All the curves were done at 1200 Fahrenheit. And in hours, the creep strain was measured inch per inch. And each of these experiments took 80 hours, right? So if you think a work week is kind of 40 hours, this is 2 work weeks of time. So it's probably actually longer than that with the setup and all of that for each of these curves, right? So if you think about the labor that's involved in somebody collecting all of these curves and instrument time and overhead and all of that, these are valuable curves, right? So we are given a series of stress levels that is applied to this component at a constant temperature, 1200 F. And we mentioned, I think I left my squares on there for one of these. Okay. Okay, well, it was the time hardening one, so that's fine. So I went through the time hardening rule, in which we take time to be continuous, and then we add up the incremental strains. Okay, so this is my slide that I was working from last time. It doesn't look exactly like the one that I was writing from, but it has the same values on there. And so you can see now that my orange boxes that are on the screen are continuous in time. So 10 hours, 20 hours, 20 hours, 10 hours. And all we did was look at the dimension, the Y dimension of each box, right? And that is the creep strain that we would expect the component to experience over that time. And then we add up those increments of creep strain to get some total. And we had a good question at the end of the last class, which was if this cycle of stresses continues, like this is some mission, then we could divide by, we could take our total creep strain that we're allowed, you know, like 0.01, and then we could say how many times can we go through this cycle to reach that, right? So it might make sense based on prior analysis just to say, oh, well, we would just take the number that we got, 0.004, divide it into 0.01, how many cycles do we get? But that ignores all of the time history that we've already had with this part at a high temperature. And so really what should be done if this mission cycle goes through again at an elevated temperature through these stresses, at time equals 60, which is where the overarching mission cycle ends, it drops back down to 1,000 psi. We really should start back on this curve here and go another 10 hours. So that would be kind of like here. So it adds a very small amount of strain. And then after that, we should go up to the next curve for 20 hours, right, which is behind my writing here, but it would be yet another box. So the amount of incremental creep strain we add over time diminishes, right? And so it's hard to say whether we would actually reach some maximum creep strain if we had multiple repeated mission cycles here. We would need more data beyond the 80 hours in order to see that. Another thing we could do is fit this data using some sort of logarithmic function and say, if the logarithmic function holds up to 80 hours, I'm assuming it holds past 80 hours, and then I'll calculate, because I can extrapolate out to however many hours I want, and then I can determine whether all those summed up creep strains would surpass the limiting creep strain, in this case like 0.01. So it's a great question about continuous stress cycling under creep strains. Okay, so that's the time hardening rule. So remember this value that we got of 0.004. So we'll compare it with other methods on the next couple of slides. The next rule we can use is called the strain hardening rule. And in the strain hardening rule, instead of the time being continuous, the strains are continuous. And so it's much easier to add up the strains because we just go up the y-axis and that's our total creep strain, okay? And so if we go back and think about the levels that we had 1,000 psi for 10 hours, and then 2,000, 3,000, 4,000 for 20 hours, and 10 hours. That's our mission cycle here. The first amount of creep strain that we get is exactly the same, right? So we have 1,000 psi, we go out to 10 hours. We look at where that hits. I think before I said it was like 8 times 10 to the minus 4, something like that, right? It's less than 0.1% strain. Okay. Well, now we're not going to start at 10 hours and go on like in time hardening. We're going to do strain hardening. So we're going to start at this value of 8 times 10 to the minus 4, but we're going to jump over to the other stress curve. So I'm going to jump over back to the second stress curve, and I'm going to look at where that hits in time. So that hits at about, if I'm at the 2,000 curve, it hits at about, I don't know, 3 hours. Right, so I want to go 20 hours, so I got to go out to about 23 hours. So I'm going to follow the second curve out to 23 hours. Okay, and then I'm going to look at the incremental creep strain from that segment. And I'm not actually going to quantify it because you'll see now that we're just going to keep adding up on our creep strains. Unless they overlap or something like that. But we don't drop back to 1,000, so we're okay. Now we go up to 3,000 psi, and we start wherever we intersected, wherever we left off in the creep strain that had accumulated so far, and then we go 10 hours. So we're here, that is at about a time point of 12 hours, let's say. So we have 12. We add on 20, we get 32. So we're going to go out to about here on the third curve. So we're going to go up this high here, follow it over for the third increment of creep strain. All right, so that's adding up pretty nicely. And then we have our last phase, which is another 10 hours, but we're at 4,000 psi this time. So we'll go back to the 4,000 psi curve, drop down, and see that we are at about 15 hours. Add on 10, that's 25. Go up to that on the last curve here, and then follow it up until we reach that point and come across. All right, so these are all estimates, but in this case, all of our creep strain is continuous, so we just go to the highest value, read it off. It's between 0.005, 0.006, right? Let's say like 0.0052, right? Something like that. Okay. So that one's pretty straightforward. If we had to go back down to a different stress level here, these strain ranges on the y-axis would overlap a little bit, so we'd have to keep track of the initial strain and the final strain and take the difference between those two. We can't just assume that oh no, actually we don't. It should all continuously add. That's the point. Okay. So here we get 0.0052, and the other one we got 0.004. Okay. So for strain hardening rule, we would expect a little bit higher total creep strain. And in this case, instead of really taking into consideration the time history, we're now considering the strain history to be more important as we add up the strains, right? So if we have alloy X here, we don't know what it is, but we look up general information about it and we find out that creep strain is usually controlled by the strain history, we're going to use this method. If we find it's usually controlled by the time history, we use the prior one. Okay. So those are the first two. And then the last one we have is called a life hardening rule. And so this one tries to sort of mishmash the other two together in a ratio for each level. And I thought I made the chart bigger here, but for some reason I did not. Okay. I'm going to stop and just make it bigger so that things are a little easier to see here. Hang on. To like 60, less than that. Okay. All right, better. So I cropped off most of the plot, but it's still the same. It's still the same plot. So the life hardening rule has us looking at the life that is, let's say, the time that is allowed for each strain, and then how much of that time have we occupied, right? So it involves thinking about some asymptotic ends here. So I did, in fact, end up fitting logarithmic functions to these, so that we could think about how much life there would be, how much life we can get in time in hours that is beyond the 80 hours that we were given, okay? So the life hardening rule says that we basically have this, we break it up into initial and final points. So we're going to have the first phase, the initial point, and then we will have let me set this up slightly differently. Hang on. Okay, so we're going to have the initial point, which I'm going to call lowercase li, and then we're going to have a final point, which is lowercase l subscript f. Okay, and this is really easy for the first phase, because it's the same as the other ones. So our initial L1, and these are in time, in hours. So the first one starts at a time of 0 and goes out to a time of 10 hours, because that's what we were given. And then we know we've already calculated what our strain increment for that one will be. Hang on. I should have laid this out on the slide first here. Okay. So that's going to be in hours. And then we'll have our incremental creep strain, which was 8 times 10 to the minus 4. Okay, that doesn't change. Our first phase is the same for all of these. Okay, so how do we calculate where we start the next one? Well, we come up with a factor, which is the life we would expect for the next level we're going to, divided by the life we would expect for the level we're at. Okay, and so the equation that the book gives us, they say that we suppose this ratio holds true, that our initial start point for the second phase divided by L2, which is a long life. Give me 1 second here. Let me make sure I have this right. L2, L1. Ah, yes. Okay, I got it. So it says that we suppose our starting point for our time for L2 as a function of how long we could expect to have our second stress level to reach the critical creep strain, right? So I'm going to write that next to this. Okay, so capital L2 is hours of life at stress level 2, I'm going to call it. That's how long we could possibly hold this thing. So that's why I said I had to fit these curves to logarithmic functions to get that. And so we say, suppose this ratio is equal to the first, where we ended our first time, because this is a history-dependent thing, divided by the hours of life we could get at the first stress level. So basically, we're going to provide continuity through this ratio. So that's the life that we are taking into consideration. So I'm going to go and draw the first box like I had before, because that's goes out to 10, goes up to kind of 0.008. Okay, so that was our first box we had for the first phase, delta 1. So now we have to calculate where the second phase is going to start. So we're going to take our hypothesis here, our supposed hypothesis, and we are going to solve for this L2I. So L2I, that's where we're starting next time, is equal to the ratio capital L2 divided by capital L1 times where we ended up last time, our little L1F. So we use the first phase to calculate where we start the second phase. Okay. So in order to get these, I had to fit some logarithmic equations to these and then solve for what would be the amount of time to get up to this creep strain of 0.01. So I'm just going to write those equations on here. So all of them are logarithmic functions. So this top one is y equals, I'm going to write this compactly, 0.0026 natural log of x minus 0.0022. Okay, so that's it's just a fit. I basically took 10 points on each line, used a plot digitizer, and then fit a logarithmic function to it. They all fit fairly well. The second one was y equals 0.0018 natural log x minus 0.0017. The third one is y equal 0.0014 natural log x minus 0.0016. And the lowest one is 0.00072 natural log x minus 0.00068. Okay, so unfortunately we got a lot of zeros because we're working in the strain realm. So I fit those functions, and then I said, okay, if I'm going to solve for x in each function, what is that time for y is equal to 0.01? Because that's the critical creep strain we were given. All right. Okay, so for each phase, I got a large number of hours. All right, so I'm going to write that sort of underneath each line. So for the first one, oh no, I put these backward. Did I? 1 second. Yep, I put them backward. Sorry. All of these functions need to be swapped. So like these two and these two. But that is sort of an intermediate step to this. That's not that important. So at the highest load, we can go 87 hours, right? So that was basically on the chart. At the second highest load, we could go 680 hours. Third highest, 4,040 hours. And at the lowest load, 2.57 times 10 to the 6th, right? It takes a very long time for us to reach some critical creep strain. All right, so now we can calculate the starting point of the second box, all right, after all of that work. So we'll go back to this table that I kind of am going to make a box around so we don't lose it completely. And so now we're going to start at this capital L2 over L1 times the first one. So our L2 is going to be the 2,000 divided by 1,000. So I'm going to go to the next slide. This is too busy. Okay, so L2I, right, was L2 over L1 times L1F. And so we had 4,040 divided by 2.57 times 10 to the 6th times our 10 hours. That's where we ended last time. And we come up with something that's not much higher than 10. Or actually, yeah, it's not much higher than 0, sorry. So this ratio here is like very, very small, right? 10 to the minus 3. So it's 10 to the minus 3 times 10, it's 10 to the minus 2. So we get 0.016, and that's in hours. So we're just going to say that's also 0 hours starting. Okay. So I'm going to go back to my other slide. And so we start the second phase also at 0. And then we're going to go out 20, so we end at 20. And I'm going to draw that on the plot now. So if I take 20, and now we're at the second stress level, we go straight up to 20, draw it back all the way to 0. So if I come over, that's my strain that I'm adding for the second stage. And so in that case, I get like 0.0022, something like that. So we're going to go 2.2 times 10 to the minus 3. And then we're going to do this again. I'll go to the next slide to calculate where we're starting on the next line series in time. Okay, whoops, next slide. Okay. So now L3I is equal to capital L3 over L2, that's where we came from, times L2F. So that's going to equal 680 divided by 4,040. And we ended at 20 hours. So we do that, come up with a value of 3.4. Okay, so we're not starting too much higher than we started last time, but now we're on that third curve. So I'm going to go back to here. I'm going to write 3.4, and I go out to 23.4 because we go 20 hours. Draw that on the plot. So we're going to go from kind of 3.4, 23.4 on the third line. I'm gonna go up to like here. But I didn't start at 0 that time. I kind of started where that other box ended. So I'm gonna draw that along here. So our delta 3 looks like that. And I calculated that to be 0.0026 approximately. So let's write that on our chart. So 2.6 times 10 to the minus 3. And then we only have one more to go. So we'll go back here. So L4 is equal, 4I is equal to 4 over 3 times L3F. So that was 87 hours divided by 680, and we ended at 23.4. So our new starting time is 3.0. So this one, that's why this one is confusing. We continue to like overlap in all of our starting boxes. So we're going to start at 3 hours for this last phase. So I'm going to put a 3 here, and then we go 10 hours up from that. So we end at, not 10, 13. There we go. And so it's going to get a little bit hairy on the box over here, but if I start at 3 on this line, I go out to 13, gain quite a bit of creep strain on that one. Go here. Come on, pen. All right, so I'm just going to draw a line from here to here. And that's our fourth one. So you can see now it gets very messy with all of these like overlapping regions. And so for region 4, we have like a change that's about 2.1. So we're adding on very similar values here. So we got 2.1 times 10 to the minus 3. Okay, so this one, we started on all of our ranges kind of a little bit lower than we did on all the other ones. So if we sum all of these together, right, we get 0.0077. So we get the highest value that we've gotten so far. So in terms of a history, the life hardening rule takes into consideration sort of the time history, sort of the strain history, but it does not mean that it ends up between our other two estimates for the total creep strain. That's just how it compensates for the history. We actually would predict a higher creep strain for this. So in this case, we could say that based on the data we're given and based on the stress series that we were given, we could say that the life hardening is the most conservative. Right, we predicted the highest creep strain. So then if we had to extend that out, it would be the shortest life. Then next most conservative would be the strain hardening rule. And then the least conservative would be the time hardening rule. Okay. So that's the example of just taking the different models for cumulative creep strain. Questions about that for now? Yes?
Unless otherwise specified, which one would you choose? I mean, you're reading all off the same curve, so you kind of, all three can be applicable at the same time. So is there any indicator which one's more accurate, which one's better? Is there one that's widely accepted to use more?
So the question is, what's the starting point, right? If all of these could apply, is there one that you always do first, kind of back of the envelope? And the answer is, it all depends on the material, unfortunately. So we're given that this is just some alloy X, right? We don't know what it is. We don't know if it's ferrous, non-ferrous, if it's aluminum, if you know, titanium, whatever it is, we have no idea. And so the approach would be to see if there's a general characterization of the material already as to what part of its history, whether time or temperature, has more impact on the creep strain, and then go with that method. An alternative approach would be to try to determine that information yourself from a complementary set of data. So this data was done at a constant temperature, but different stress levels. And you can see that we can fit logarithmic curves to this. We can also go back and calculate that Larson-Miller parameter, right, for some failure state. Like, here's the maximum creep strain, here's the temperature over whatever, 80 hours. That's the maximum parameter I can get. Or you can find complementary data that's at different temperatures but the same stress level. And you can see how much each one of those contributes to this Larson-Miller parameter, because all it is a multiplication of two terms. One is temperature plus a constant, the other one is log of time plus a constant, right? And so you can think about those two, the product of those two, and which one is driving the process more. And then make that like your sort of reigning understanding of that material and which approach to use. So, yep, unfortunately I do not have more idea than that. So I wanted to start introducing dealing with combined creep and fatigue. So I'm just going to go to a blank slide. Next. Oh, I don't have a blank slide. Okay, maybe after? Nope. Okay, here's a blank slide. Actually, I'll go. This will be our motivating slide. So we're going to start thinking about combined creep and fatigue. And this is not something that occurs for most components that we would be using here on the ground, because we normally would try to design for infinite fatigue life, and then we don't have elevated temperatures unless we create those elevated temperatures. But there are high performance applications. We'll do an example of one at the beginning of the next lecture, which is aircraft gas turbine blades, and things like nuclear reactors and things like that always have high temperatures. And so they really have to take into consideration both of these effects. Okay, so we're going to cover it just first sort of qualitatively, and then we'll put some sort of quantitative backing to it, and then do an example problem. Okay. So this is a nice chart that the textbook gives us to try to motivate any trends we could possibly find between low cycle or high cycle fatigue and creep strain. Okay. So this is a data from a lead alloy. Okay, so if you know anything about lead, you know that it is just trying to write lead, that it's a softer element, and even when you add it into other alloys, it's still not going to be able to be like a super, super hard material. So we would expect that this is a good material to study because it may have very high creep strains. Like you can see here, 0.1, right? So that's a percent, it's 10%, so 0.1. Our other in the last example problem, it only went up to 0.01, right? So high potential creep strains here. All right, so let's look at this curve in detail and see what it is telling us. Okay, so the x-axis is in time, and it's in minutes. Okay, so kind of 0 to 50 minutes. So it's not a long time. It's not even an hour. It's less than an hour. So it's a short time, but these are accelerated tests to really emphasize the effects that are seen on a material on which we would expect them to be emphasized. Okay. The y-axis is creep strain. And so we have a first curve here. So at 0 minutes, a creep strain or a stress is applied to the sample, and the creep strain is recorded. So that's not really a creep strain at that point. It's an instantaneous strain, and it's already almost 3%. So it's quite a high stress. And we're going to call that stress level 1, sigma 1. So all samples have the same sigma 1 over 5 minutes. Okay, so just boom, 5 minutes. There will be some creep during that time, right? Even higher than 1%, because sigma 1 is probably fairly high. Then at 5 minutes, we're going to jump and apply a different stress, and that stress is going to be sigma 2. That could be higher than the original stress. That could be lower than the original stress. So this would be like a constant temperature experiment, but with changing stress levels, right? So this is kind of going to give us an idea of, okay, now if I have not just changing stress one time, but I have it 10,000 times or 3,000 times or whatever, what might I expect to happen? And then after that, I think they go back to like sigma 1. Okay, so those are the 3 phases after 25 minutes. So those are the 3 phases. Okay, so what are all these different series of curves on here? Well, curve 1 they have this inset here, which is a little bit of a crazy inset. I don't know what the y-axis is, but the x-axis is a ratio of sigma 2 over sigma 1. That's the x-axis down here. So if I look at point 1, which corresponds to the very top curve, it tells me that my secondary stress, my second stress, sigma 2, is higher than sigma 1 because the ratio is greater than 1. So that's all I can say for that. So if we have an initial stress level, we hold it, and then we pop it up to another stress level, sigma 2, that's higher than sigma 1, we get an acceleration in the creep strain initially, and then a logarithmic decay. Okay? Well, what if the ratio is about exactly 1, right? So what if it's not greater than 1? What if we're just holding the same stress? What does that look like? Well, if we hold the same stress, then there's no change. The ratio is 1.0, and we're at line 3. So line 3, I'll highlight it here, is a nice continuous line. It doesn't really have that accelerated rate, right? It just continues on with its logarithmic decay. Okay, that makes sense. And then there's a line in between. And then if we go down in the ratio, so actually we have a high stress level, we let it creep for 5 minutes, then we drop the stress level, what happens? We're not dropping the stress level such that we have a lot of like elastic deformation. So the creep strain does not decrease, but rather the rate of it decreases. So if I circle that here on the plot, then we don't have an accelerated rate there for sigma 2 less than sigma 1, but we have a decelerated rate. So we almost go back to some other trend that's not even a logarithmic function. It looks more linear down there, right? And the magnitudes are very low. And then if we go back to our initial stress level after 25 minutes, then we do see that secondary accelerated creep there. And so this gives us an idea that it's not only a function of the stress change one time, but rather the stress change kind of every time, right? And if we look and compare sort of the lines on the right side here, we see that, okay, if they follow along with our stress levels, and our secondary stress over our primary stress drops going this way, we can see that, whoops, there's sort of some interesting things going on right here. Just where the stress levels drop a little bit and then go back up, the magnitudes of our total creep strain, so just how high does this thing go at the end of the test, 50 minutes, right? Oh, maybe that's what that plot is there. Ah, okay. They sort of have a little bit of a dip, right? Where the ultimate, the sort of total final creep strain dips down and then goes back up and all this thing. So it's like, okay, how do we predict like our final creep strain given some stress history? Well, it's not straightforward how to do that. And so this is just sort of a motivating plot that the textbook gives us for this specific lead alloy that would be very susceptible to this. So the magnitudes are all super high, the rates are very accelerated, whereas with more, let's say, hardened engineering materials, you would not expect the magnitudes to vary quite as much. If you want to view this in some kind of a cool 3D way, the book gives us this 3D plot. Generally, I don't agree with 3D plots unless they're absolutely necessary. But time goes this way, and the ratio of the second stress to the first stress is on this other axis here. So the highest curve that we saw before went up like this, and then up had a very accelerated rate, whereas if we got down to where it equals 1, kind of had a continuous curve, and then if we dropped our stress, we went up initially and then flattened out and then went up again. So you can see that this curve is not, it's not monotonic on the z-axis, let's say. So that's what this whole contour plot here is supposed to show you, that this is a non-monotonic total creep strain. Okay, so if we said that our cumulative creep strain in the past depended on material properties and what class of materials in, this also is similar. And so our textbook here actually walks through, I'm going to go 6 or 7, maybe more, different materials and what their typical behavior is. But it does not provide that in a chart. It's all in the text, right? So I'm going to summarize a little bit of it in a chart for you. So here it says, I'm just going to read this one sentence and then I'll start summarizing. It says, diverse results have been reported for creep tests under cyclic stress conditions depending on the alloys and test conditions used. And then they've looked up basically a whole bunch of papers that are well cited that give some different behaviors. So I'm just going to write them out here. So we've talked a lot about SAE 43 or 40x40 type steels. And so this one is a paper on SAE 4130 steel at an elevated temperature of 430 degrees C. Whoops, 430 degrees C. And they say they did an hour of high stress, then an hour at low stress. And they concluded that for this material, which is more typical of engineering steels, cyclic stress interruption, they're calling it. So cyclic stress interruption, if creep strain is a process to be interrupted, had no significant effect on the creep strain. Let's call it creep strain with a delta there. Accumulated at this high temperature. And then they say, on the other hand, an aluminum alloy subjected to the same type of comparative test, okay, even though it was very slightly different, found a different effect. They found that under cyclic testing, the creep strain was 3 times higher than for a static test or a static load. I'll just write an equals here. I'm not sure, right, or greater than. Is, equal to 3 times the creep strain for a static load. And so you can see that for a hardened steel, the effect is negligible. For an aluminum alloy under similar testing conditions, they found a large effect. So this points to the fact that it really is material dependent. They mention a titanium alloy called RC130A, right? Titanium is kind of can be like a Cadillac of high strength to weight ratios for aerospace applications. They measured that the elapsed time to failure increased by a factor of 5 if the load is removed half of the hours that it was tested. Okay, so they got 5 times the life. And they actually didn't do a true sort of creep strain experiment on this one, but rather they were looking at the stress rupture time. Right, and it does not say what the temperature was for this experiment, but it was a high stress level for 80 hours. I'm assuming it was high. So stress rupture time increased by a factor of 5 when the stress was cycled. So they give us these 3 materials to tell us that the effect can either be, it can be one of these 3 ways. So it can be negligible, right? And that would be really helpful because then we can analyze our lifetime separately from creep strain, right? They don't interact. There's no combined effect, and we already know how to do a lot with fatigue lifetime predictions. Now we know about creep, right? So we just have to see which one will be like a limiting factor because they don't interact. But we can keep those sort of separate, okay? For the aluminum alloy, right, we would say there is a negative effect of the cycling, sorry. So there's a negative effect, or that would be a combined effect for a negative result for a shorter life. Okay, and so there is some interaction, and it reduces the lifetime if it has those cyclic conditions. And then for the titanium, they actually said when the stress is cycled between those 2 values compared to held there, the rupture time increased by a factor of 5. So that's a positive effect. So it's combined for a longer life. Right, so these are actually just, if we had to try to generalize something about how these things combine, we can't do it because we use aluminum, we use titanium, we use steel, and so we can't assume that the same observations are always going to hold. Okay. That said, if we know some values, we can put together some rules to use in order to figure out the strength of this effect. Okay, so we're going to end this lecture here, and then I'll talk about a quantitative way of thinking about this, and we'll start problem 1313 to sort of demonstrate what we've learned so far in the course and a quantitative way to handle this.